I say a 43%? No. Do you guys know how many points your test was actually out of?
70.
So actual points on it, though, was out of 43. I scaled it to being out of 75. So if you got 43 out of 43 on your first AP set test, how'd you do?
Good job.
You would declare that, right? Yes.
Yeah.
Okay, so we need to know things to be able to make a comparison for how this person is doing. And that's what we're going to do a lot with the normal distribution. It's used to compare things that are not easily comparable. Like the decathlon scoring is one of the easiest examples. How do you compare throwing the shot put and running the 100 hurdles? It's not the same thing to compare, but we can find the average and standard deviation and actually make comparisons on which and stuff. Okay, so let's look at the notes. So first, we're looking at measures of location. So if I talk about a quartile, you're just thinking about your box plot. Like, where is Q1? Made a little box plot. Let's know which of those little values is Q1. The edge of the box. Yeah, the left edge of the box over there is Q1. That's the 25th percentile.
So the percentile closer to 100 is better. So if someone goes out and brags they performed first quartile, they performed first percentile, they're probably right. If someone brags that they managed to get first percentile, then they're probably right.
Okay.
Oh, I got it.
Yes, I know. Never a dull. All right. That's okay. You see it hanging on the board like Yep. You're tall enough. All right, and then percentile, you guys have seen percentile scores a lot with like your PSAT. You get that information back and you're like, oh, I'm in the 96th percentile. That means that 96% of the scores are below yours. Okay, so whatever the percentile is, if we're talking, let's say 90th percentile.
And hence it's impossible to get a 100 percentile because you can't be better than yourself.
This means that 90% of the scores are below your score. Okay, so it's all about a position. It's a location. You are thinking 0 to 100. Where are you on that distribution?
I will.
Okay. If we don't have everybody's data, we can estimate it based on the mean and standard deviation if our data is normally distributed. Okay, so we touched on density curves just a little bit in the last unit. Just remember these are for a random variable. And what we're doing with this is going from a histogram to a curve. So if you think about it, you have your nice little histogram. We are turning that into a curve. Okay. For description, all you're doing is describing or describes the overall pattern. Of a distribution. And then some properties. We're going to just touch on these quickly because we're not spending a lot of time on them in Unit 2, but they are things that we'll come back to in later units. So first, your area between values is the proportion of observations that fall in that interval. So the area, if you were to find the area under the curve, you know, all your calculus knowledge, you're looking at what percent fall in between those two kind of barriers there. What do you think the total area under the entire density curve is going to be? It's 1, because it's 100%, okay? And then just a few details. The curve, it never crosses the x-axis. For what you're doing in statistics, the height of your curve doesn't really mean anything, so it doesn't mean much. I'm never going to ask you anything about the height of your density curve. And if you were to find the area under a single point, kind of like back in geometry, it's 0. There is no area to find under one specific point. Okay, so then some different density curves that we're going to look at throughout the year. This unit, we will talk about standard normal curves, and we'll keep talking about those for pretty much the entire year. Okay, we'll talk about z-scores, so it's a z distribution. I think you guys know the shape of a standard normal curve. It's what you think of when you talk about a bell curve. It's perfectly symmetric. T-distribution is something that we're going to get into later. It's similar to the normal distribution. It's similar to your normal curve. But it has heavier tails, so like the tail ends of it are fatter than the normal curve. With T-distributions, we'll talk about degrees of freedom. As your degrees of freedom increase, it gets closer and closer to the standard normal curve. But again, that's not anything for this unit. That's something we'll come across again later. And then the third one there, the chi-squared distribution, that is one that's always skewed right. And again, that comes much later in the year. Right. So far, so good. Any questions so far? I know that's pretty kind of just definition stuff so far. All right. So let's think about our standard normal curve. If I say standard, that matters. If I'm talking about standard, this second point here, this N01, matters a lot. If we have standardized it, we've put the mean at 0 and we've made your standard deviation equal to 1. So this right here, the 0 is your mu, and sigma is your 1. You can have normal curves without standardizing them, but if you standardize it, you always have a mean of 0 and a sigma of 1. You know, it's bell-shaped. The mean, the median, and the mode are always going to be the same if it is a standard normal curve. Okay, they're all right at that peak in the middle there. We're not going to worry about the inflection points right now. The empirical rule, you definitely need to know that. Okay. Anybody know what the 68, 95, 99.7 means?
In a normal shaped curve, within 1 standard deviation, 68% of the data sets will lie. Within 2, 95% will lie. And within 3, 99.7 will lie.
Perfect. Yes, that is exactly what that means. So let's make a picture of the standard normal distribution. So since it is the standard normal, what's going to go in the middle? What's my mu? 0. Okay. And put in some markings here. So my standard deviation is 1. So if I go 1 standard deviation above the mean, I'm at 1. Okay. Then I'd be 2 standard deviations away, 3 standard deviations away. If you go to the left, you're talking about negative values. Okay. And again, this is for the standard normal distribution. You can certainly draw it without standardizing, and we'll do some of those. All right, so I know that within 1 standard deviation is 68% of the data. So how much is in each of these little bands right here? 34, yeah. The whole thing's 68, so right in there's 34. Half of 68, we can do that, right? All right, so each of those 34. What do you think it's going to be for the next being 2 standard deviations away? We know all of it is 95, so what am I going to find in each of those little sections? Close. What do you think, Alex? Not quite. 13.5. Good. How'd you get that?
95 minus 68.
Yes, 95 minus 68 divided by 2. All right, getting stranger percentages. What's the next one going to be? $2.35. Good. Okay, and then that very last section. Close. 0.15. So your tiny little tails there are 0.15%. Okay. All right, so if you're talking standard normal curve, that's what you're looking at. So let's look at this example down here. We're going to talk about IQs. They're normally distributed with a mean of 100 and a standard deviation of 15. So you could note that as N100, 15. That means normally shaped, mean of 100, standard deviation of 15. So we want to make a sketch for the IQs. So I'm going to go ahead and erase what I did along the x-axis here, 0, 1, negative 1. You can just write it below it if you want to leave those there. It's up to you. So the mean is 100, so I'm putting that right in the middle. Now if I'm just 1 standard deviation above that, what IQ score would correspond to that? 115. 2 standard deviations above. 30, 3 standard deviations above. All right, and then going the other way, what's one standard deviation below 85? 2 below? 70, and 3 below? What do we say? Subtracting is hard, I know. 70 minus 15? 55, okay. All right, so I want you to now use what we've labeled along with the percentages we've talked about with the empirical rule to answer these 2 questions for me, okay? Take attendance while you guys do those. Shouldn't take you too long. All right, guys, so what percent of individuals have an IQ lower than Forrest Gump?
2.5% of people more stupid than,
Hey, Becca, it's just...
sorry, 2.5%. Maybe I'm more stupid than saying that.
All right. And then using our empirical rule, what percent of individuals have the IQ between 100 and 130? We can add, right? 47.5%, okay? So the empirical rule works nicely if you're talking about values that are exactly 1 standard deviation or 2 standard deviations away. We're obviously going to look at questions where it doesn't work out quite so perfectly, okay? But questions on the empirical rule, pretty simple. Okay. All right, so let's think about our mean and standard deviation. So if we're looking at the mean, we know the mean is always the peak, right? And if we change the mean, what do you think is going to happen to the whole distribution? Like if the average and the mean increases, what happens if it stays normally distributed? Yeah, it's a shift. So we could say changing the mean results in a horizontal shift or translation. Okay, and then our standard deviation, we're talking about the spread of our data points, how, on average, how far away each value is from the mean. If that gets bigger, if your standard deviation is bigger, what do you think happens? This. So we could say the larger the standard deviation, the wider the spread of the normal curve. All right, so looking at these three curves, can you guys tell which one's A, B, and C? Do you want me to color code for you?
Wait, sorry, never mind.
Do you need me to go back up there?
What does the mean change?
It's going to be a shift. Like if the mean increases,
Left
it
to right.
shifts to the right. Yeah, it's a left and right horizontal translation. So A is this one, guys. B, this guy. C is obviously the other one. Okay. All right, so using A, B, and C, I want you to answer these two questions. You're going to order the curves from the largest mean to the smallest mean, and then from the largest standard deviation to the smallest standard deviation. Okay? All right, largest mean to smallest. Everybody together, what should the order be? CBA. That was definitely everyone together there, right? CBA, okay? And then talking about our standard deviation, largest spread to the smallest. What should the order be?
A.
CCA, good. Make sense? Okay. All right, so identifying the normal distribution. This is something that you are absolutely going to do on free response questions on the AP exam. Later in the year, we'll get to checking conditions, and one condition is stating that your distribution is normal. So there's a couple different ways you can go about that, and again, we'll look at those as we get further into the year. But you will absolutely talk about things being normally distributed. It can be given to you. You can actually use your data points. That one, be careful if you talk about a histogram. So let's say they give you a set of values and you plug it into your calculator and you look at the histogram and you say the histogram appears to be normally distributed. They're going to want you to sketch the histogram, okay? The normal probability plot, that's something I'm going to show you on your calculator probably next class. You can just look at that and say, okay, the normal probability plot looks pretty linear, and you can just state that as your reason. You don't have to sketch it though. Okay, so I think that's the easier way if you're going to look at your data values. You could calculate the empirical rule also, but then you're telling them 68% of the values fall between here and here. I don't think it's the easiest way to go about proving that something's normal. Okay. If they give you the graph, you just have to talk about the shape of the graph. Does it look approximately normal? That's what you're doing there. Okay? So those are how we identify that, yes, this is a normal distribution. Okay. So we have 20 students. They were asked to guess the age of somebody in a photograph. Are these guesses approximately normally distributed? Okay. So let's put the values into your calculator. Maybe I will show you today the normal probability plot. Go ahead and get out your calculator. Let me find mine. So go ahead and start putting these values into your list one. If you don't have a calculator, does anybody not have one? I have no idea whose calculator this is, so come borrow it. Your calculator just died. That's, oh, it just is dead, okay.
Now what do we do?
Hold on. So guys, first go ahead and just look at the histogram of these values on your calculator for me. We're not going to sketch the histogram or anything like that. I just want you to decide, does it look normally distributed
Where
or
do we do that?
if you go under your stat plot.
That count?
Nope. Okay. Let me get this up here. All right. If you go second stat plot, does everybody have their data values in? Second, do you have your points in?
Yes.
Do you have your list? Okay. So then if you go up here, this is second y equals, takes you to your stat plots. Okay.
Histogram.
Yes. Look at your histogram. What do you think about the histogram? Does it look pretty normally distributed? Yes? Okay. So the next one I want you to look at, we've picked histogram. Now I want you to pick this very last one. Okay. This is your normal probability plot. I have my data from list 1, and then I always just leave this on the x-axis, where it's going to be plotted. Once you have that, go ahead and hit zoom 9 for me. This is our normal probability plot. Does that look pretty linear? Yes. If this is pretty linear, then you have normally distributed data. Okay. We'll use it later to look and see if something is random, but right now what we care about is the normal probability plot appears linear. Okay. Anybody not getting to this point on your calculator, please let me know if you don't know where I went. Yeah, don't be shy. I know sometimes you look up and you're like, pretty straight line, right? Anybody else? Okay. So what you would say, answering this question, are they approximately normally distributed? I would say the guesses are approximately normally distributed. And our reason is the normal probability plot, and I'm going to put that in quotes. Okay, that's what we just graphed. Shows a fairly straight line. Is it going to be perfect? No, you're not going to see a perfectly straight line or perfectly normally distributed data, because usually what you're looking at is actual real data values, and those are never perfect. Okay, so you'll notice we're always talking about something being, you know, roughly symmetric, approximately normal. Okay, always include those like, yes, it's pretty close to that, but it's not exact. Okay, that's, you always want to have that in there when you're describing your distribution. Okay. All right, using our standard normal curve. This is quite possibly the most important thing you'll learn all year for everything that we do. So I know lunch is coming in 15 minutes. We can make it through this, right? All right, standardized scores. We talk about z-scores a lot. So the first bit of caution, don't assume data is normal. Okay, don't make that assumption. You will either be told this is normally distributed data and then you don't have to worry about it, or if they just give you a set of values, you need to check. Okay, take a quick glance at the histogram, look at the normal probability plot. In some way you need to determine, okay, yes, this is actually normal data and I can use the z-scores. If it's not a normal shape, you cannot use the formulas for z-scores. It doesn't work. The percentages don't line up. Okay? All right. So what we use for the z-score, I have two different equations for you up here. This is the one we're going to use the most right now. So it is whatever your score is minus the mean divided by the standard deviation. Okay, that's what we're looking at. This is the more complicated version, but it means the same thing, because what we're doing right now, we are looking at like one individual score. If we want to know how your SAT score compares to everyone else, what's the mean of your one score? Just your score, yeah, okay? And what would n be if we're looking at your score alone? 1, and what's the square root of 1? Sigma divided by 1, okay? This matters later, but for right now, everything we're looking at, I would focus on this formula right here. It's definitely simpler, and it's got everything in it that we need, okay? This is how you find a z-score. How many of you remember doing z-scores in like Algebra 2 forever ago, a little bit? Yes, some of you, it wasn't as long ago as others. So, okay, yes, it's the same idea. We'll obviously do a little bit more with it, but it's the same basic principle. So what a z-score is telling us, it's telling us the location, okay? It's so we can make comparisons, where you are in position compared to other people. Same pieces of information. All right, so let's look at the first example here. Mike's trying to decide if he should send his ACT score or his SAT score off to schools. They give you here, the SAT scores are normally distributed with a mean of 1,500 and a standard deviation of 250, and then ACTs normally distributed with a mean of 21, standard deviation of 6. I know this is from a few years ago. I don't know if that's completely accurate for where we are right now with scores, but just so you know. So what we're trying to do is figure out which of those scores is actually better. Should he send the 1,700 or should he send the 24? Okay. Do you see both of them are above the mean, right? We're just trying to figure out how far above the mean as far as which one is better. So let's find the SAT Z-score. And we'll find the ACT Z-score. All right, so for the SAT, what was his score? Okay, so 1,700 minus, what was the mean? 1,500. Divided by, what was the standard deviation? 250. So what do we get for our Z-score? 0.8, good. Okay. Then for the ACT Z-score, what was his ACT? 4 minus 1 over 6. So what do we get there? 0.5. Okay, so which one's better? The SAT, yeah. He's closer to 1 standard deviation above with his SAT than he is with his ACT. Okay. All right. So we should send this SAT. Okay. We can also figure out exactly what percentile he ranks in both of those. We're just going to look at the SAT, but that would be another way you could compare is which percentile is higher. So we're going to use our calculator again for this. Let me get mine back up here.
Make a direction.
Grab the pass. There's my mouse. Okay, you're going to go ahead and pick second bars. This is going to take you into the distribution menu. Okay. We are looking at normal data right now, correct? We are going to use number 2, the normal CDF, okay? It's the normal cumulative density function, so pick 2. All right. Couple ways we can look at doing this. We actually figured out his standardized score. We did the 0.8. We know how many standard deviations above the mean he is. So I can go ahead and leave this as the -1 e to the 99. That's basically talking about really far to the left. Okay. Up to where was his score? What did we come up with as his Z-score? I'm sorry, I should phrase that better. 0.8. So let's go ahead and put in a 0.8 there. Since we're talking about what his Z-score was, not just his straight SAT score, we've already standardized it, so we can use the 0 and the 1. And then let's go ahead and paste. You're going to figure that out, okay? Yeah. It's not doing that. Okay, yes, you have labeled numbers, so you else calculator troubles? Okay, so what do you think that 0.788144, what does that mean? Yeah.
78 percentile.
Yeah, I would round it up, I'd say almost the 79th percentile. Yeah, exactly. So, remember we did our norm CDF, Mike ranks. What about the 79th percentile? Now, what if we hadn't taken the time to find his z-score first? Do you think there's another way I could have done this? I can get in there. What'd you say? Yeah, so he scored, what did we say, 1,700? If I just want to go to the raw score, and we know the mean was 1,500. And the standard deviation was what, 250? We get the exact same thing, right? Okay, so it all depends on how the question's asked. If you've already had to find the z-score or not, you can certainly do either one of those. Okay, that makes sense? Okay. Now the next one, it says, what percent of individuals scored higher than Mike on his ACT? I want you guys to try this one. So I'm not asking his percentile, I'm asking what percentage of people were above him. Okay? Could you find this person? Yeah, it's about like 30. You find a good person, There are other ways to get there. Yeah, they know.
Okay.
Right, the whole thing would be one.
Yeah.
And you'd be like, you don't do that all the time.
You only be up to the 99 percentile, but that the whole curve itself is 100. So I was like, not sure which number.
You just hang that back up. No, pads. You just hang your pads back up. Back in. Yes, thank you. Okay, walking around. Oh, did we get there? All right. How about? Did we get about 31%? Or higher than 90? So if you told me, what did you tell me, like 30.68 or something? 30.85, that's fine. If you were more precise than that, that's okay. Again, do you see I'm saying about 31%, or you could say approximately. We're not super concerned with the exact decimal value, which is very different than so many of your other math classes I know. But we're just looking for roughly how many scored above. Okay? All right, we'll pause there. Lunch is coming. All right, guys, let's look at the next section here.
Where's roll bunch?
On the back shelf, guys.
Yeah.
All right, I want you guys to try this one too. What percent of test takers score between a 23 and a 27?
I don't know if we need to go look.
Not like All right, guys, try this first one.
SAT, so 0.8, and then since on the answers, we keep and then if you do all that, then you get 70.
Yeah, I get that.
And then for this one, you do very well, that's the highest, that's the lowest.
And it shows like
And so you put in the 1 times 1099 as your buffer, and then at the lower, you put in this. And then that will get you 30.85. And for this one, I did like, because that's the third between these two, I put the lower, the 3 and the 5. And then for this one, it's like, really different than these stuff.
maybe it just needs it. Leave it alone. How are we doing on this one, guys? Okay. Is it standardized for your doing zero?
Oh, actually, it's 23 to 22.
Oh, so that makes
I'm really good at putting the wrong numbers in.
oh, my gosh.
I did that on my mom, but I said like 3 stories.
I thought you had to choose like subtracting or adding.
Yeah, 25 plus 100.
Okay.
How do we determine what percentage of people are from 23 to 1?
Okay, here's your North CDF. And where's that? Second cars. North CDF. So from one C score to the other.
Yes.
0.33, 21.
So if you, so two ways you can do it. You standardize your by 9.25.
So then you would use nil. The scores, 21%. The
You could have done from 23 to 27.
All right, let's try the other one.
Yeah. Make sure. You think so? Did you get 21?
Did not.
Okay.
Which didn't mark severely. This did end up being slightly different. This ended up being slightly different, but I guess it was just rounding error.
Yeah, if you put in that, that'd probably be exact.
It's like 0.3.
All right, guys, walking around, it looks like most people got there. If you need to, make yourself a picture. We know the mean was 21, so 23 and 27 are somewhere over here. I want to know what percentage is in there. Does it make sense that 23 is the min, like the lower, and 27 is the upper? And then your mean is 21, your standard deviation is 6. Some of you standardized it and found your z-score so you could use the mean of 0 and standard deviation of 1. If you want to do that, that's fine. Just make sure you don't mix. You can't use the 0 and the 1 if you're talking about 23 and 27. Okay, you've got to keep it, either we standardized it or we didn't. So this was about 21%. Okay. All right. I actually want to stop. there for right now and give you a little bit of classwork today. What I want to do, is this all we have left? Is street video?
Yes, I think so. Well, I can get that.
I know, we're almost through the whole unit, guys. All right, let's finish. Okay, so next, we're going to try to work backwards on this one. So Sally's discussing her score. She knows she got in the 75th percentile, so she knows she's somewhere up here, right? And we want to know, what did she get on her ACT? Remember that ACT is normally distributed 21 and 6. All right, I want you guys to work on this and try to figure it out. How are you going to get back to the score? There's a couple ways you can do it. Okay. There's a long way and then a really easy way. Do you want to mess with the long way, or do you just want me to show you the really easy way?
Really easy way.
You just want to get to the easy way? We have 20 minutes left. We can do that. So the long way, you can actually take the time, find her z-score, then calculate how much area there is up to that z-score, what score corresponds with that. You can do all sorts of stuff with that. You don't have to do that. You can use your calculator to help you with this. So if you're looking for a score, you are going to use the inverse norm. Okay, you're working backwards this time. So go ahead, that is under that distribution menu as well. So we're going to pick the third one. And again, hopefully you have the nicer calculators. Hopefully you have any calculator that works, right? We're talking about 75th percentile. So does that make sense that we're going to put 0.75 up there? And then you know your mu and your sigma, right? 21.6, plug it in. And this will give you her score. So she got a 25 on her ACT. This is what we did. We did 0.75. We did the mean. So Sally scored 25 on her ACT. Okay. All right, so if you know the percentile and you want to work backwards to the score, it's inverse norm. If you know the score, you want something to do with the percentile, that's the norm CDF. Okay? All right, let's look at the last one here. All right, works cold. It's approximately normally distributed, the weights of our dogs here. So we can say N, mean of 77, standard deviation of 6. All right, I'm asking you for the IQR. So go ahead and find that. Think about what IQR tells you. What is the IQR? Do you know what it is? Okay, what is IQR? Okay, just Q3 liner for a certain percentage. Yeah, yours, just about it.
Wait.
Calculator border. Okay, so that's your backup. I can't spell. And your phone is over there, so your No, think about it. It's a standard deviation of 17 represents one standard deviation range. Okay, so I keep walking. And okay, try to fix it. Yep.
You mean you're all okay with
Let me check on it, see if it's, we gave, we left alone for a while.
The problem is they all wait for him, like they all wait for him, instead of like he was lying.
Nothing. Look at their little. Okay.
Yeah. Which is why they're not like.
All right, guys. So for this one, the IQR of Labrador weights is about 8.1 pounds. Okay, again, keep practicing context for the question. Get in the habit so that just becomes automatic. All right, so walking through this, how did you figure it out? What is IQR? Interquartile range. So Q1 to Q3, what percentile do those line up with? 25th and 75th, right? So then what did you do? Okay, found the weight that corresponds to the 25th percentile and the weight for the 75th percentile, and then subtract them. Okay, and it's just over 8 pounds. Okay, well guys, there's unit 2. We're cruising right along here.